Hi, my name is Jerry. In this short presentation, I'm going to talk to you briefly about IPv4 subnetting, variable length subnet masking and supernetting, why it's important in communications, why to do it and how to do it. The first thing I want to talk about is the structure of an IPv4 address. Before I go there, I just want to show you briefly the 7-layer model and the 4-layer model. So we're talking about IPv4, which is the network, the internet layer. IP is a central protocol in communication. So that's what I'm going to be talking about today. Right. An IPv4 address was designed with a 32-bit address. Each bit can be a 1 or a 0. These are easy for computers, but more difficult for humans to read. So what we do is we split the 32 bits into 4 groups of 8. And each of the octets group of 8 can be represented by a decimal number between 0 and 255. An example here is 192.168.10.1, and we can see that 8 zeros in binary represents a decimal 0. 8 ones in binary represents 255. So all of the numbers in the octet will vary in a range between 0 and 255. We'll talk about that in more detail in a minute. Right, we have to talk about positional notation. In decimal, this is easy to understand. Every shift to the left represents a 10 times increase. So the example I like to use is 365, which will be 3 hundreds, 6 tens, and 5 ones. In binary numbers, we adopt the same principle, but every time we shift to the left, we double the number. So this grid is useful. Starting from the right, 1, 2, 4, 8, 16, 32, 64, 128, we're doubling every time. And that will show us how to convert decimal to binary and binary to decimal. So in my example here, I've got a decimal 192. So what I've done is I've put the numbers, each of the constituent parts of the number, under the grid. I've got 128 plus 64 and no other numbers. My next example is 128, which is a bit more complicated. My next example was 168, which is a bit more complicated. I've got 128, 32 plus 8. So to convert, we can either line the binary number up under the grid and convert to decimal. To convert decimal to binary, we use the reverse. So in my example here, I've got 144, and if I take the largest number I can from the grid, from 144, I get a remainder 16. This was a nice easy example because 16 appears in the grid. But if it didn't, you would keep subtracting each of the numbers from right to left until you had the binary representation. Now, at this stage, I'm going to look at some interesting patterns when we're converting decimal to binary and binary to decimal. So here's my grid, and there's a decimal 0, binary 0. Binary 1, decimal 1. A decimal 3 is a binary 2 and a binary 1. So that's represented by 6 zeros and 2 ones at the end. Binary 7 is a 4 and a 2 and a 1. Can you see the pattern there where if I've got a continuous line of ones from right to left, the result is one less than the leftmost number on the grid. So 7 is 8 minus 1. 15 is either 8 plus 4 plus 2 plus 1 or 16 minus 1. And And that pattern repeats all the way to 255. Another interesting pattern is when we're moving from left to right, that's clearly 128. 128 plus 64 is 192. If I add a 32, I get 224. Plus 16 is 240. Plus 8 is 248. Plus 4 is 252. Plus 2 is 254. 1 is 255. These numbers are interesting and useful when we get to subnetting because our subnet masks are continuous from left to right. Next, I'm going to talk about the subnet mask. Subnet masks are useful because they're used to show the network part of the address and the host part of the address. An IP address on its own isn't very useful because you don't know how much of the address is the network and how much of is the host. So that in using conjunction with the subnet mask, we can tell what network the address belongs to, the size of the network, where the network begins and where the network ends. In the original classical networks, they were simple. The network part was either the first 8 bits, the first 16 bits, or the first 24 bits. These were useful. These were simple, but not very useful because we wasted a lot of addresses. We had big networks. Today we want to have smaller networks, which are more convenient and waste less addresses. The subnet masks for classical networks were either 255000 for 8 bits, 255 for 16 bits of the network, or 255 for Class C 24-bit networks. Waste IP addresses. So in order to stop the waste, we started using VLSM, variable length subnet masking, or classless interdomain routing. The subnet mask can be used to calculate the network or subnet ID, where it will just show the network part of the address. All of the host bits are 0. And we can adduce the broadcast address by switching all of the host bits to 1. I will show you a couple of examples of that in a minute. Once we know the subnet ID and the broadcast address, we can tell the usable range. The classic example of this is if you've got 2 IP addresses and subnet masks, you can calculate whether they're in the same subnet or not, which is a useful thing to know. Right, I'm going to show you a useful table which I would recommend if you're doing exams where you have to do subnetting. You would need to be able to reproduce this from memory. So the first line is 1248.1632.64. We use that to convert from decimal to binary and binary to decimal. The next thing we need to know about is the subnet mask. A memorable fact is /24 networks have a subnet mask of 255.255.255.0. They've got 254 usable addresses. That's a fact we'd need to memorize. Now, to have smaller networks than /24, the next example would be a /25 network. The subnet ID is now 255.255.255.128. We've got, so if we split a /24 network into /25, you've got 2 networks of almost half the size. If we wanted a smaller network, we could go to /24. The subnet mask is now 255.255.255.192. If we follow that example using the numbers we saw a couple of slides ago, we know all of the valid subnet IDs and the size of the networks. The smallest network you can have is 255.255.255.252. It has 4 usable 2 valid addresses. Now, those black lines represent subnetting in the 4th octet. You could subnet in the 2nd or the 3rd octet, and those would be the slash notations. We will look at those briefly for supernetting at the end of the session. So that is a useful table. I would certainly recommend that you memorize the red, the green, and the first black line. There is a blue line, which is the number of valid hosts for each of the subnets in their last octet. So a /25 network would have 126 valid hosts. The reason for that is that each network has two reserved unusable addresses for host addressing, the subnet ID and the broadcast address. So that blue line will be valuable later when we do variable length subnet mask design. Right, here is an example. I've picked a random IP address 10.214.244.76 with the slash notation of /24. Now we know from what's gone before that a /24 network means that the first three octets of the network, the last octet is the host part. So your subnet mask will be 255.255.255.0. Simple. If we convert the IP address into binary, I've highlighted the fourth octet because that's the one I'm most interested in this example. The subnet mask, and then if we AND those together. Now, ANDing is a simple process where we take the two inputs and we calculate the outputs. If both of the inputs are 1, the output is 1. If any other thing happens, i.e. either of the inputs are 0, the output will be 0. So if we AND 01001100, which is the binary representation of 76, and the binary 0, we get an output of 0. The observant of you will notice that if the subnet mask is 1, the output will be the same as the input. That's useful to know. The broadcast address we can calculate by switching all of the host bits, the 8 zeros in this case, to 8 ones. So that gives us the output, that gives us the result that the subnet ID is 10.214.244.0. The broadcast address is 10.214.244.255, and the usable range is one more than the subnet ID and one less than the broadcast address. So if your IP addresses are in that range, they're in the same network. Now, here's another example. This time, I'm going to change the subnet mask from /24 to /25. And this time, the IP address will not change, but the subnet mask does. When we AND the subnet mask and the IP address, the AND doesn't change. Now that's interesting, because in this case, the broadcast address is different, but the subnet ID stays the same. So in this example, if we take a /24 network and change it to a /25, we've got two possible cases. It's either 0 to 127. If my number 76 had been greater than 127, the subnet ID would have changed, the broadcast address would be 255. For my next example, I'm going to change the /24 to /26. Now, if I take a /24 network and change it to /26, I will have 4 smaller networks. The subnet mask will be 255.255.255.192. The first two octets, the first two bits of the last octet will be 1s and all the rest will be 0s. The binary IP doesn't change still, but the subnet mask does. When I AND them together this time, I get a different value, because now my my subnet ID is 64. The broadcast address is also different. So that was a simple representation of, that was a simple explanation of how you do subnetting. I will make a spreadsheet available where you can use random addresses and slashes, or you can type in your own numbers and see how they end up. So it's a good practice tool. The next thing I want to show you briefly is variable length subnet masking. It's another kind of thing that you may be asked in exams. In this case, you were given a set of networks. In this diagram, I've got 4 networks A, B, C, and D. But notice that each of the networks is joined together by a separate network. The red lines will represent a point-to-point network, which will have two usable addresses. So this will be a /30 network. The address space will be given. Now, the address spaces will be private addresses, so we can use as many or as few as we want. So if you run out of addresses when you're doing VLSM, you just use another address space. What's critical here is when you're given the number of hosts, you will decide on the smallest subnet ID, because you want your subnets to be small and secure. And then we will calculate the subnet ID and the broadcast address for each network. Don't forget the links. So in this example here, I've got an address space of 192.168.20.0/24. I've got 4 networks which I've allocated random numbers of hosts. So what I will do first is I will rank the networks in order of size. We do this conventionally so that it makes your VLSM easier to do, because you're allocating the larger networks first. It makes sense. So I'm going to go back to the table that I suggested we used a couple of slides ago, and I'm going to use that table to decide what is the smallest network I can have, the smallest subnet I can have for each network. So in my first example, network A needs 74 hosts. If I look at the table, I'm looking at the blue line. So I want the smallest blue number that is larger than 74. So in this case, it would be /25. For network C, which has 25 hosts, I can use /27, and so on. So I can work down through each network and find the smallest slash network. Once I've got that done, once I've done that, I can allocate a subnet ID and a broadcast address to each network. The broadcast address is a subnet ID plus the block size, the red number -1 for each subnet. If you exceed this space, you can use another, as there are private addresses. So if you run out of addresses in the address space, you can just use another private address. The last thing I want to show you in this presentation is supernetting. Supernetting is useful and important because you can use it to aggregate smaller networks into a larger one. Makes routing tables smaller, which is good. So what we will do here in this example is we will identify the bits that don't change. So in my example here, I've got 3 /24 networks. So we can see here that it's the third octet that's changing. So what I will do is I will extend the third octet, I will convert it from decimal to binary, and I will identify which bits are the same and which bits are different. So my red line here shows me that in these three networks, the first 6 bits of the third octet are all the same. So I can simply use my table to say 192.168.20.0/22. So this puts all of my smaller networks into the same network. Okay, in this presentation, I've explained what IP addresses are. I've explained briefly how to subnet, how to do variable length subnet masking, and how to do supernetting. Along with this presentation, I will make available a spreadsheet where you can practice examples. I hope you've enjoyed this presentation.